Alrighty, thanks a lot for being here today. So it's a real pleasure for me to introduce Professor Gabriel Chen from Hope College. So Professor Chen is an expert in clustering, machine learning in general, and in particular spectral methods. He just transferred 1 year ago, maybe, from San Jose. Yeah. Now he's in Michigan, Holland, and he previously been in other institutions. I think he had a PhD from University of Minnesota. He worked under Ilan Nerman. The only thesis on spectral clustering for linear modeling. He has a bachelor and in bachelor in mathematics and statistics from the University of Science and Technology of China at Hefei. He held other positions, in particular, I just mentioned San Jose, but has been also at Claremont McKenna College, visiting there. He's also been visiting Duke, and I think was a postdoc position under Mauro Maggiore, and who's now at Johns Hopkins. And he has so the tool set is gonna describe are very important for many applications. Several of you guys are working on supervised learning method on financial applications. You can feel free to. I encourage you to consider these methods for your work on that. And I stop wasting Professor Chen's time. So thank you for being here.
Oh, thank you. So that's really nice introduction. You didn't ask me about my my information. I wonder where you got those information. Normally, right, the person who invites people, you ask how do you want me to introduce you? Right, can send me a paragraph, and you didn't do that. Yeah. Anyway, yeah, I'm really glad to be here. Yeah, and thanks again for the invitation, for the introduction. Yeah, so it's a really warm day, right? So it's really good to be here. So today I'm going to talk about some new past work, also more recent work on the scalability of spectral clustering. So I'm not sure whether everybody has the background, right? So I'll spend some time talking about what spectral clustering is, right? How does it work? I'll show a demonstration. Then I'll point out some computational challenges. Yeah, that's why we have the second part of or maybe also the third part of the talk, right? So I think today I'll try to focus more primarily on the speed part. So for two reasons. I think first, I added some new slides after I arrived here, so to show more applications. So that basically take more time here. I'm not sure whether I can get to the last part of the memory scalability in 45 minutes. But secondly, I think also fortunately, I submitted a poster last year to talk about this memory scalability. So if I don't get to that part, you have my poster, right? Okay. Then I'll try to summarize and conclude and point out some new future directions. So how many of you have heard about the spectral clustering? Like, do you know? Have you heard about it? Like, okay, not very many, right? Very few. So basically, spectral clustering actually refers to a family of clustering methods. Okay. So all these methods, they are common in one thing, which is to build a similarity matrix on a given data set. Say you use the vectors to represent the data points, but they can be also images, documents, right? Like or any kind of objects. But basically, I need to be able to measure their similarity, pairwise similarity. So this way, I can represent all the pairwise similarities in a matrix denoted by W. Right? W is also called a weight matrix later because W defines a weighted graph. Okay, so Wij is the similarity between your object I and object J, right? And kappa is your choice of a similarity. So it could be Gaussian or cosine, or it could be simply nearest neighbor similarity. So if they are within key nearest neighbors of each other, then you give them like a large weight like 1, right? If they are not within nearest neighbors of each other, then you give them a weight of 0, right? Okay. So basically, you pick your weight to choose weights, then you can generate such a matrix W. Okay. Then after that, I think this way the different methods will kind of differ. Okay. So there are also different perspectives about spherical clustering. I think one popular perspective is to regard clustering as a graph partitioning problem. So because we talk about W, right, that has the pairwise, similarities. Okay, so then if Wij is positive, then you should connect the object I and object J, right? You can add an edge to connect the two. Then collectively you have a network. Okay, so the nodes are the original data points. The width indicate how similar those nodes are to each other. Okay, then you get a network. So for each well-defined cluster, you should have a dense network, right? So then if you have a clear separation between two clusters, then these two parts of the network should have few edges, right? Few edges, and also hopefully also small widths. Okay. So now clustering is equivalent to a graph cut problem. So I want to be able to partition the graph into two parts or three parts, so that I have a minimal loss of edge width. In the meantime, I also want to make each component as dense as possible, right? So that's why we have a different criteria to measure how good the cut is. Okay, so I think so you have ratio cut, normalized cut, min-max cut. I think I'm going to focus on normalized cut because it has really nice theory. It also has a connection to the graph Laplacian as a matrix. Okay, so here we have some terminology like the degree matrix. Okay, so starting with the W matrix. So if I sum up each row of W, I get a so-called degree. So for example, here, so this corresponds to one row of the matrix W, right? Then these edges will give you the non-zero entries of that row. If I add up these edges, I get the so-called degree of that node. Okay, that is the total edge width around this vertex, this node, then measure the connectivity of the node to the rest of the graph. So I'm going to sum up each row. I use the row sums as to occupy a diagonal of a diagonal matrix. Okay, so that matrix is denoted by D, the degree matrix. Okay, so that's a diagonal matrix. It contains row sums of W, which measure similarity, or local similarity of the nodes. Okay, now next, if I let D and W subtract initially, I get a third matrix called the graph Laplacian. Okay, the graph Laplacian actually is really interesting object. It has many nice properties. Okay, it reveals a lot of information about the underlying network. Okay, so then also sometimes we want to normalize the graph Laplacian by the degree matrix either on two ends, on the two sides, or on one side. We have two normalized versions of the graph Laplacian. So this one is a symmetric normalization. This one leads to a rule stochastic matrix. Okay, that's the rule scaled version of W. So basically W has the width, right? So if you scale the rows of W to have a sum of one, you have a transition probabilities. That's what I call by P, right? So rule stochastic matrix.
So the second one, we use it for something which has particular directionality.
Particular
Directionality.
Directionality, what do you mean?
Like, for example, that your flow of information from one location to another more often than reversed. Because the first one is symmetric, so I guess that if you use that to compute the distance, then distance of AB is equal to distance VA. Well, in the second case, it's not symmetric anymore.
So the second one is not symmetric, exactly. This one is symmetric, this is not, they are similar matrices. Yeah, here, I think the rows of P, these are really transition probabilities, at each node. So I think I have another thought about directionality. Yeah, but they define how like a person, say, if they were to explore the network according to this normalized.
It's like something like that. It's unidirectional in one case, not unidirectional. In one case, it's bidirectional. Right?
Oh, I think I see what it is. So basically, this one defines the Markov chains random walk, right? That's one direction. Yeah, that is like this node. This probably differ from this one. Yeah, right, yeah. Okay. So basically, there are a lot of matrices right behind. So that's why linear algebra is really important. So that's really my favorite subject. Okay. So how many of you have taken like one semester of linear algebra? Okay. Well, if you haven't, yeah, you should take. Yeah, you should really take one because that's really like a very useful tool. Yeah, especially for for CS people, right? They also need to know linear algebra. Yeah. Okay, so basically, yeah, we have a lot of matrices. Okay, so why do we care about these matrices? So it turns out that different versions of spectral clustering use different normalizations. Like this version of spectral clustering using the symmetric normalization W. Then we use the top eigenvectors, top eigenvalues. Okay. Then the top eigenvectors will perform a transformation embedding of the graph into a low-dimensional space. Okay. Similarly, the normalized color algorithm can be shown to use this P matrix. Okay, that's the one-sided normalization. And because P is similar to W2, okay, then the eigenvectors so are connected by this degree matrix. Okay. And also here we have some random walk perspective. If I generate a random walk on the graph, right, let a person to stand here, that person will choose a random edge to move along, then that person will keep going, right? So you can say for a long time, that person will be probably trapped in this part of the graph. But after a long time, that person maybe will occasionally go to the other part of the graph, right? So then you can basically control how long you let a person walk along the network. Then you can get diffusion coordinates in like the given number of time steps t. Okay, so again, it can be computed based on the eigenvectors of W2 eigenvalues degrees. Then you can find the different coordinates. They measure global connectivity information. Like after a few steps, this person can travel as far as here and also as far as here, right? Like that person will be able to tell, okay, these nodes are all kind of densely connected. That's one cluster. Okay, so different coordinates allow you to look at the data at different scales. Okay, so here, let me show you a cool demonstration. Right? So originally, my data set has points along the three circles. There was no coloring. So everything is dark black. Okay. So the goal of clustering is to be able to separate data set into three groups. Right? This is one group. There's a second group. There's a third group. So clustering, the goal of clustering is to color code the data according to the pattern here. Okay. So so if we give this the data set which is unlabeled right, to some other algorithms like k-means or EM right or mixture modeling, actually that's really challenging. If we go through if we compute the weight matrix, then we take the top eigenvectors, the top number of clusters. So then in this new space, I have a low-dimensional representation of the three groups. Okay. So the red circle, all the points are sent here. All the points in the blue circle, they are sent here. All the green points, they essentially become one point. In this space, you see the clusters are revealed or are also made easier. So there's a lot of separation. Also, the clusters are really tight inside each part. So that this way we effectively perform clustering, we can use k-means to do the job. Yes.
Is spectral clustering used a lot when there are patterns in the data?
So it doesn't actually, it only new. So what takes input is really this W matrix. So that's pairwise similarity. So in this case, so we could compute, basically we could compute all the pairwise similarities, like how similar are these two, how similar are these two. But I think a lot of times we just need to focus on local. Basically, we just need to know locally these are similar, these are similar, these are similar. As long as these are well connected, that things will propagate. You will be able to tell overall these are all similar. Okay. So basically, the reality, I think we restrict the calculation to a local neighborhood. For every point, you look at the similarity to a few nearby points, then you keep going. So that you want to actually use the.
It's like if you compute the distance, right? You're gonna see that the distance between the red dots is gonna be small. So you
some are small, some are large, but you want to be able to decrease very rapidly.
Right.
Yeah.
While whenever you compute the distance between the red and the blue, they're gonna be always large.
So it's not so large compared with this.
Oh,
yeah, that's why here I think there's going to be like a bandwidth parameter. That's going to be important.
And that's gonna appear in the matrix W.
Yeah.
Because in one of the entries of the matrix W, between the two observations, you're gonna see a number. Right? And based on those numbers there, you see this, then you're gonna have different properties of the matrix. And because of those different properties of the matrix, you're gonna have the clustering, very nice clusterings that you see there.
Yeah. I wish I could. I should have showed the display the matrix as the image. So basically, each cluster it gives you a block of the matrix. So this block is very dense. This block is kind of like it's like a zigzag. It's like so because there, I think if you restrict your calculation to local neighborhood, so that's one block that will correspond to like a circle. Okay, but still overall, right? You see, these are gradually shift. These are still overall similar. So knew that there's really a lot of details behind spectral clustering. Okay, so but it's a really, I think it's a really beautiful new method. It's really effective, right? So this is just one example. So now you can imagine how these clusters, how they curve. As long as they are, each one is well connected and overall they don't intersect. So spectral cluster will always transform into a space like this. So the clusters are all made much smaller in size. They are also well separated. Okay. So that's the advantage of a spectral clustering. But then but on the other hand, spectral clustering can be slow when you have say a large data set. The main reason is the size of W. That's N. So nowadays we kind of have thousands, tens of thousands, or millions of data points. Right? So W will be a million by a million, right? For a large data set. So then we have to compute eigenvectors, eigenvalues. So things are slow, costly. Yeah, that's why there has been a need to develop approximate spectral cluster algorithms so that they are fast and they are still accurate. Okay, so that's why scalability becomes a like a research topic or focus, right? So here I'm going to show you some work I did in the past. I have to say this is not too new because I came here, I think, to provide a gap for the memory scalability part. Okay, this is more on the speed scalability. And I address this in two steps. So first, I focus on spatial kind of similarity, that's cosine similarity. That's about the angle, so like 2 points. If they have a small angle, then they are similar. If they have a large angle, then they are not so similar. Okay, so that's how you compute the cosine similarity. So each row times column gives you a dot product. That's the cosine of the angle. Okay. Then we subtract identity to make the diagonal 0 because we don't like self loops in spectral clustering. Additionally, I'm going to assume that X has some sort of low dimensional structure, like it could be a bunch of documents, or it could be a bunch of small images. Okay. When the document is smaller, right? So the matrix is most sparse. If we have a bunch of small images, overall dimension not too large. Okay. Basically, I need this assumption to make the spectral clustering here. I will develop a linear complexity algorithm. Okay. So what if it is not does not have this? Well, you can always do principal component analysis for your data into a few hundred dimensions. So that is always it can always be made a low dimensional, okay, relative to the size of the data. Okay. Then I will show that spectral clustering in such a setting can be performed based on very simple efficient operations. So there's no big matrix W, there's no expensive calculation like the eigenvector, eigenvalue decomposition. Okay. In step 2, I'll try to talk about how to extend this from cosine to any similarity, like Gaussian. Okay. So the techniques to use a bunch of landmark points to transform this back to cosine. So cosine is always there. Okay. Okay. So now let me tell you, the first part, right? So scalable spectral clustering with the cosine similarity. Okay. So let's recall assumptions, right? So we have a data set n points in d dimensions. So these are already normalized. We have unit norm, right? So that's for computing the cosine of the angle. So if they are unit vectors, the dot product will be cosine of the angle. Okay. Then X is either row sparse, that's for documents data, or it's of a moderate dimension. The dimension is relatively smaller than n. So that will be satisfied by small images, right? A collection of small images like this. That will be n, that will be b. Okay. So b is much less than n. If in general, you can always perform PCA, right? So then cosine similarity, that's as the matrix, X transpose minus I. Okay. So what I will try to show is the following. So I will show that no matter whether it's this version of spectral clustering or in-cut or diffusion maps, they can all be implemented efficiently based on three kinds of operations. Element-wise operation. These are all linear complexity operations. Matrix vector multiplications, still linear complexity, or low rank SVD, still linear, and as k number of clusters. So let's see how we can do this. So definitely we will need to look at some math. Okay. So basically the idea is to completely avoid W in the implementation, but it's still there. It's still behind the scene. Okay. So first, if you recall how we compute the degree matrix, that has the row sums of W. So W is the matrix. One is the vector of ones. So each row of W times the boundary of ones. Sum them up, let's take the row sum. So if I know that in this case W has this product form, okay, so I have this W times 1, I'm going to distribute, and more importantly, I want to group these two together. If I don't do it this way, that will be expensive matrix multiplication. If I'm going to regroup this way, that's matrix vector, that will be a vector, that's going to be matrix vector again. It's two matrix vector operations. There's no more matrix multiplication. Okay, I can get the degrees based on two matrix vector multiplications. And afterwards, because assuming eigenvector W2, so now let's look into the expression. We have this times W times that. So then you can see I have a different level half here and also here. So I'm going to group them together. That's a normalized version of X. That's the transpose. So I have X cubed times X cubed transpose. So X cubed is d negative half X. So they have the same signs. And we have exactly the same zero entries. That means if X is a row sparse, X cubed also is a row sparse. Okay, so I will preserve both the size and also the sparsity pattern of X. Okay, so we just got this. Okay, so you have to know some linear algebra, as I said. Right? If we didn't have this term, okay, so eigenvectors of W2 would be exactly that singular vector X cubed. Okay, that would be trivial. Okay. Now I have got like a perturbation term, d to the d inverse, right? The degrees. Okay. So how do I handle that? Know that my goal is not to really build the W2. I want to compute eigenvector X cubed directly from X cubed, not compute the product. Okay. So here are a few observations. So I'll maybe talk about this one. This one. So how do you understand the term d negative 1, right, d inverse, that's really a perturbation. Okay. And also, if d inverse is gone, right, then we just use SVD on X cubed. Okay. But d inverse there. But here I want to point out that if the d inverse or d has a constant diagonal, then I can still discard it, because if it's a constant diagonal, that's going to be a multiple identity. That subtracting that just shifts eigenvalues, but does not change eigenvectors. So if all my degrees are more or less the same, then I can still safely discard d inverse. Okay. So let's so basically we will need to equalize the diagonals as much as possible. So as to
saying constant diagonal means that diagonal of D you have the same value, correct?
So ideally, yeah, in general it's not true. Yeah. So ideally, if all the degrees are the same, I mean, all the points have the same connection, same amount of connection, then D will be a multiple of I. So D inverse will be also a multiple of I. Then, so I don't care about eigenvalues, I only care about eigenvectors. I will just discard those. That does not affect eigenvectors. So let's look at an example. This is the calculation based on the 20 units group dataset. Later I will give you more information. Basically, that has roughly 20,000 documents. So then I computed the inverse degree, but 1 over the degrees. So I plotted them. You can see if they were all the same, I should get something flat. I have got this part plus a more flat part. So what are these points? These points, so they are large in terms of the inverse degree. So actually, without inverse, they are really small. These are the points that have really small degrees. So what are those? They are outliers. Outliers, right, tend to be far from the majority of data set. They have small degrees, but their reciprocals are going to be large. Actually, they show up here. So if I discard this part, you can see I will just clean up my data, right? I will remove some outliers. You can see the rest of the curve is actually relatively flat, approximately flat. This is where I will start discarding that term. So basically, I'm going to discard a small fraction of the data, like 1%. Then I will show you 1% will be already enough. Okay, so I'm going to discard 1% of the data as outliers. For the rest of the data, then typically I will have such approximity that will be reasonable. Then I will be able to safely discard the inverse. I will just focus on x cubed. That will give me approximation to eigenvector x w cubed. Okay, so that leads to the following algorithm. So basically that's my data, right? So ideally sparse or of a moderate dimension. Rows have been normalized. I have 3 choices for the third clustering. And for now, I need to know the number of clusters, and also I need to be able to remove a small fraction of the data as outliers.
So moderate dimension could be something like n, like hundreds of thousands of individuals, for example, with d maybe hundreds of variables.
So basically, d needs to be 1 magnitude smaller than n.
Well, at least one mark.
Yeah. So
be 100,000 customers and 1,000 features of the customer, that would work.
So yeah, if if the ratio is 10 or more, but basically
At least 10.
Yeah, maybe, but it's that's empirical, but basically asymptotically, right? So you do over n goes to 0. That's right. That's how you quantify that. Yeah.
Yeah.
So basically, when we have a complexity of the form ND, so n is dominant, d is very small, so that's considered linear. Yeah. Right.
So, and the other thing I want to ask is, in practice, by careful use of even not super advanced linear algebra tools, you end up, instead of computing a n times n matrix product, you just do a much lower product. And that's where you say the computational time. Is that correct?
So you can do the low rank eigenvalue decomposition.
Right. So what I'm trying to, so what I'm thinking here is this, that through the use of, in practice, the matrix is used to naturally reduce the dimensionality of the problem, because in practice what you end up doing is just simply computing the distances. And through a careful use of linear algebra tools, in practice, instead of doing matrix products of high dimension, you are able to do matrix product of lower dimension. And so the computational cost is decreasing. Is that correct?
Yeah, if you reduce dimension, yeah, definitely, yeah.
But I mean, when you do the matrix product that you do, you end up carefully regrouping so that the cost of those products is lower. Is that correct?
So I mean, this part is essentially element wise, because that's a diagonal matrix.
Right.
That's just modifying entry individually.
But that product is now lower dimensional, right?
That product is still of the same dimension, like d is the diagonal square. So that's m by d, that's m by n, over that's still m by d. But then this part is actually also efficient because these are diagonal. So basically this one is, I think it's scaling the I think this one is scaling the rows.
But what's the purpose then of eliminating, not counting the matrix d at -1? Why is it important to just add that d -1 doesn't count for the eigenvectors?
So that's that's a d inverse or d -1. That's a different formulation with spectral clustering. So here I think I'm focusing on the symmetric normalization, but I think there will be a way to go to the d inverse.
So if I'm wondering like that, these couple of slides, right? You practice also the next one maybe. You had a series of maybe later. No, I think it's later.
Later.
The one, yeah. Maybe the next one.
No.
This one. Yeah, this one. Okay.
This one, yeah.
So my understanding here is that the important thing of this slide is, if you want to understand the spectral properties of W tilde, you now to understand the spectral properties of X tilde transpose.
Correct.
But if the computational cost doesn't decrease, why is that important?
So if it doesn't decrease, it
It
decreases.
decreases, right?
Yeah.
Why does that decreases?
Because so that's n by n, that's n by d, but if d is
That's what I'm talking about. So instead of having an m by n matrix to compute, you have something which is lower dimensional. Because it's n times d times n.
right.
And so that's, and one is the transpose of the other. So
Correct.
the rank of the matrix is lower.
So basically the idea is to work directly on the matrix without multiplying the transpose. So basically you give me x, I'm going to just do some simple things, yeah. Then I will give you what you need.
Right, because the spectral properties of x transpose of x transpose x tilde x transpose tilde are the same basically of x tilde, right? So the things which are important, right? And so you can just go to x tilde, which is n times d and d smaller than n.
Yeah,
And so at the end you go from n dimensional stuff to d dimensional stuff.
exactly, that's correct.
And that's where you gain.
Oh, yeah, all the d is large, but if it's root sparse, then you basically
Those
still,
parts is small. And so you gain computation.
it's still roughly low dimension if it's root sparse.
Right.
Yeah,
Yeah, I apologize for disturbing the, but I will need to really, so I'm a bit concerned about throwing away those so-called outliers.
Yeah.
So let me give you an example. Let's say we take an MNIST.
yeah,
And in MNIST, some digits 3 could be written in a way that they resemble 8.
Yeah.
Or, for example, some people write 1 and it looks like 7. Right? And those are they considered to be outliers?
so no, we have to think about the setting. I think if you are thinking about classification, we need every point there, right? For clustering, so this I'm focusing on the main part of the cluster. Actually, later we'll add them back. I will reclassify the outliers back into each cluster. So that's
So when at the inference, when I need to cluster a new data point, and let's say it's a 3, like weirdly written 3, which looks like 8, will your approach be able to identify it as like properly cluster it as 3, or will it put into 8?
I don't know. It depends on the two, like how well the two clusters I found are separated. Right? So yeah, basically, and in my model, I think in my class, each cluster has a lot of good points, maybe a few outliers.
All right,
Yeah.
they don't necessarily need to correspond directly to class set, right? To like, doesn't have to be 3, doesn't have to be the class 3,
So
right?
it
And
depends.
it's a mixture.
And focus on the good part of each cluster to figure out it's a cluster. Then we will add the bound like outliers, but I'll see which cluster fits it well. Yeah.
Okay.
So and also it's really a small amount, like 1% would be enough, right? Okay, so yeah, that's my technique. Then you can see these are the steps, right? So then we build a D. That's easy. That's matrix vector multiplications. And then we use D to normalize X. That's just entry-wise, scaling. Then we can just find do SVD, or if we have to use an entire, we just transform this by T. Then the singular vectors give me embedding. I'm going to apply k-means in that space. But remember the three tight clusters. So that's the pattern I expect here. Then the outliers are usually thrown away right now. I can add them back. Like here, I could use k-means in the embedded space, right, to iterate more. If you want to also consider they are like an influence, take them into consideration. Yeah. Okay, so now let me show you, these are basically linear complexity algorithms. Let me show you some applications. So I'm going to focus on documents data and image data. So that's a lot of documents. So that a lot of words. Right? So the data matrix is a frequency matrix. So each document is represented as a bunch of word counts. Right? How many times does each word occur in the document? And it's a high dimensional by highly sparse. Along each row. Okay. Then the handwritten digits data, these are largely sized, but they are relatively small in dimension. D is much smaller than N. These are the two ideal settings for the algorithm I'm presenting here. Okay, then we'll look at the cluster accuracy and also running time. Okay, so then for the 20 news groups, okay, I implemented the original formulation and also my scalable implementation. And also I look at two versions of 20 news. This is the high dimensional bus sparse. But I also did the SVD project into 100 dimensions. That's low dimension, right? So row sparse, low dimensional. So first row has the accuracy scored by the original, the slow implementation. The second row has the accuracy and the CPU time of the fast implementation. You can see the number is more or less the same. So this is my approximation technique. I think it gives the comparable accuracy, sometimes higher, but definitely it's much faster if you compare the time. Yes, it's much faster.
So when you say clustering accuracy, do you compare to those labels which were in the
Yeah,
training data?
this data set has the true labels. Yeah, yeah.
Okay.
I just compare with the true labels to see, to match, right? To see, what percentage of the points are in this the class I found. Yeah, yeah. So that I set alpha to be 1%. Okay, but if you want to study the effect of alpha, let's try 0, 0.5%, 1%, 1.5%, 2%. Let's remove more and more, right? You can see these curves, they are more or less the same. As long as you remove something, right? So that's 0.5%. So then you can see the accuracy of the different methods on the two versions of data. They are pretty stable, right? Flat. Okay. So that means that you have to remove a small part of the data. But doesn't matter how much you remove, as long as you remove something at 1%, then that will give you really good results. Okay.
Do you have any baseline performance of any simple classifier to come to?
Baseline for
Simple classifier which uses labels.
so I'm not doing classification here.
Yeah, I understand, but just to like how far is the clustering accuracy from a supervised learning?
These are very different. Yeah. For classification, I think you can achieve definitely like 90%, right? Because you have labels. For clustering, that's much harder. I think if you get 60%, 70%, that's considered to be good, right? Like think about it as customers, right? How do you group customers? So if you can get a 60, 70% accuracy, you have a success. Yeah. So then I also look into each class to figure out what they mean, right? So if I got a class of documents, say they are all about computer graphics. If I didn't know that, am I able to figure out the content of the cluster where I have a way to rank the words towards this cluster? Because each cluster is modeled by a line. Then I look at how the angle between each word, each dimension, against the line, I find those closest words, dimensions. So if I didn't know didn't have the name, I look at my top words that show up in each class. You can see these are all about images.
Yeah, so this is basically when similar to when you have PCA and you check the coefficients of
Yeah.
the weight of each
Right. Yeah.
Let's say that it is geographic location. Okay, so then you have a certain score there.
Yeah.
And then you put the scores over there.
Right. So this is how you make sense of each class. Right. This class is about the trucks, like all those trucks. Yeah. This class, I think that's about encryption. Yeah. So again, if you think about customers, right, you find a group of customers. How do you figure out what the group is? Right. You look at maybe the website they go to, the top websites they go to, right? Then you can figure out their interest. So that will be similar. So then also you are the ones like politics, right? Religion. Yeah. So based on the words that show up, you can tell what the group is about. Okay. So then for image data, so USPS, MNIST, you can see this one. In classification, you can get 99%. But in clustering, I could only get like 50%, 50 something percent. The slow version would be too much on a laptop. I was still able to do this, carry out this with a scalable implementation on a laptop. Yeah, that takes only minutes. Yeah, that's 70,000 images. Right, that's a lot. Yeah. So these are some new slides. One second. So I also added a application I'm still working on. This is about monitoring the water quality in the Mactawa watershed. This is actually I come from Hope College. I think that's the Holland, Michigan area. That's a big lake, Lake Mactawa. That's Lake Michigan. So there are a lot of streams that flow into I think the lake. That I think there have been like a group of people who are monitoring the species, the OTUs, how much they present in the different kinds of water, right? So then they have basically I think the abundance information of OTUs. I think that's going to be hundreds of thousands of OTUs. Then we collect water sample from the lake, the streams, watersheds, etc. Okay, so basically, the data set I got from the biology people are basically about 1,600 water samples collected in different site types across all 4 seasons. They measured the amounts, the quantities of this many OTUs. That's 200,000 OTUs. Okay, so that matrix is of the size 1,600 by 200,000. Okay, but it's highly low sparse. Like each water sample only contains at most a few thousand new OTUs bacteria. No water sample has all the new species, all the bacteria. So the sparsity of each row is at about 3.5%. Only 3.5% are non-zero. It could be much less than that. Okay. Columns are also sparse. So like a lot of columns, each column is a species. So a lot of us OTUs bacteria only was detected in one sample, one water sample. Okay. So they are a lot of that rare bacteria. Okay. So then they asked me to analyze the data and to create some visualization and also to find groups. Okay. I think this one is similar to the document data I worked on. So that's why I'm going to perform TF-IDF weighting on the columns. Okay, I'm going to pretend this is a document term frequency matrix. I will apply TF-IDF weighting, then I will be able to apply cell class with the close similarity. Okay. So then this is the visualization I created. So here I have color symbols. The colors are about the season. So red is summer, black is winter, green is spring, blue is fall. Okay, so remember that. So these are the water samples collected in summer. These are also water samples collected in summer. But the circles are those samples collected from the lake. Dots represent samples collected from the streams. You can see we have one group of water sample here, right? They tend to be, I think, from the lake. So they are collected mainly in summer, some in spring, some in fall, maybe late spring, early fall. Then you have also a group of water samples here, right? These are mainly samples collected from the streams. Then they are mainly in summer, spring and fall. You can see the lake environment is very different from the stream environment. Okay. Then you also have this more scattered part. I think that's still lake samples, but so they span, I think, fall, spring, winter during the cold time. Then you also have I think the sample collected from the streams in winter, spring, fall. Right? Yeah. So basically, I think there seem to be 4 groups. Right? So one group here, the lake in summer, stream in summer, stream in winter, and lake in transition, lake in non-simultaneous. Yeah. So I think I'll stop after this couple slides. Yeah, then I found my cluster, use my algorithm, cosine similarity. Right? I found these 4 clusters. I think these are lake in summer, I think stream in winter, stream in summer, lake in spring, fall, and winter. Then I look at the centroids, so I can look at average level of all kinds of bacteria in each cluster. That stream in spring, fall, winter, stream in summer. So the horizontal axis has all the bacteria right now. The vertical axis represents average level of each bacteria, each group. You can see, you can do this vertical comparison, right? You can see from between summer and non-summer, we have an explosion here. So these bacteria, they grow a lot. So these are still here. similarly, between Lake summer and North summer, right? I think you see this species they group. Okay, so these are the 4 clusters I found. Okay, so yeah, I think that's only the one part. I think so. I guess my times almost out, right? So let me use maybe 1 minute or 2 to tell you how I generalize to other kind of similarity. So the idea is the following. Okay, so this one slide will tell us. So you see the black points are the original data, right? So now I say I want to use Gaussian similarity. So cosine is no longer proper. This is not about angle. How do I do that? So I'm going to select some representatives locally. So I'm going to look at their similarity. So original data, my data representatives. Then I look at their similarity. How similar this one to this field? How similar this to the surrounding ones? So I have such a matrix. Okay. So basically, each row represents the embedding of the original data by the landmark points. I can now pretend or regard each row as a artificial document. Then, if for this cluster, these points and these points, they are going to be similar, right? So I have a plot here, a plot here. I'm going to basically apply cosine similarity among the rows. Right? I think I'm going to call this data documents. So these are data documents. But yeah, I could also look at columns. These are called the landmark documents. Then I can apply spectral cluster with the cosine similarity. Okay, so this works for any similarity like Gaussian or any kind of. So this number that's based on your own similarity. How similar is this and that? Where you tell me I'll put a number here. So I expect such a block diagonal pattern. Then I will apply cosine similarity.
So the matrix A though is so what I'm trying to figure out is that in okay, let me say it this way, right? So I can expand the exponential in different terms, right? 1 plus x plus whatever. So so I'm thinking that there can be a relationship with a carefully readjusted version of this and the previous matrix for the cosine similarity. I mean, it might be that if I expand in a proper regime, small sigma, something like that, I don't know. Then for observation for data sets which have certain particular structures that the approximation is valid, then you reduce the cosine similarity. So let's say that you have, what I'm saying is that there might be an expansion of this matrix A that in a certain regime goes back to the matrix W of the form X transpose X minus the identity.
So that would be something different. You probably could go in that direction. So the technique I use here is to use these landmark points to to create data documents. So to basically I do this to embed each original point into a feature vector. This feature vector is supposed to be also row sparse. It's non-negative row sparse. So these feature vectors will help transform these data points into such feature vectors. So I think of these as the keywords. I think of these as documents. So now they should.
So you do an extra step. You do an extra step in practice.
So I do this embedding step, then I apply cosine. Yeah. So then this will.
It's different from what I have in mind.
Right. Yeah.
Yeah.
So that's like a simple technique, right? So then this way I can always go back to cosine because based on this new representation, the rows, right? I just use cosine. Okay. Then I have a second algorithm. Okay, but then I don't think I have time, right? So I'm going to. I don't want to go over time. Yeah. So I did prepare a lot. Yeah. There's also another model. Okay. But also the memory part. I think you will have to read my poster. Then finally, I think let me jump to the conclusion part. Yeah. So basically, I think I was only able to tell you the scalable implementation of spectral clustering in the special case of the cosine similarity. Right? I did show application to documents, images, water samples. Okay. So there's some future work to be done. I think since I haven't talked about the memory part, I think this is let's forget about that. The basic is based. So No, this one is still about memory scalability. Yeah, the new applications. I think right now I'm working on the watershed data set. So there are tens of, hundreds of thousands of OTUs, right? What are the groups like? What can I learn from those? Okay. So then lastly, let me conclude with this slide. I think these are some of the papers that published in the past. I think that's the original paper about scalable spectral clustering with the cosine similarity. That's the general version that extends to other kinds of similarity. These two are more recent than last year. I think they are about the memory scalability. Yeah, I'm still working on this because these are still based on cosine. I still need to be able to extend to other kinds of similarity. Yeah. Okay. So yeah, with that, I think I'm going to stop here. Thank you for your time for coming here. Yeah.
Thank you. So, questions or comments, including where you can ask where you can find open source software to implement SMICs. Actually, I'll ask it.
So by the way, I think we don't have like GitHub package on this.
Yeah.
The cosine SSC cosine, if you Google this, I think there's a GitHub page that has a package in MATLAB, so you should be able to use it very easily. Yeah.
Questions?
Yes.
I just had this question about how you came up with the accuracy metric. I was just curious because my understanding when you usually cluster data sets, imagine we had two parts which got merged together. For example, you had a classification label which said it was bacteria in spring from a stream, and you had another one which said bacteria in the stream during summer season, and both of them got merged together as a cluster. How would you come up with an accuracy metric? Because I'm just curious about it because in case
Accurate. So in general, so when we do clustering, typically there are no labels. I think you have to look at other metrics, like maybe let's look at the content of each cluster to see whether that makes sense, right? So in these experiments I did, I think those are benchmark data sets. They come with labels. So say I have these three groups, right? So now let me find my own clusters. Okay, now I see, okay, a lot of points are here. So no, maybe this cluster is about this. Let's see how many of them are here, how many are not. So I have like error information. You find the best match between the two set of labels.
Okay.
Yeah.
So the data set was a clustered data set which had labels.
They come with labels. You could use them for classification, or you could use them for clustering without looking at the labels first. Right? Then you use labels to check how good your method is.
Okay.
Yeah, yeah.
Thank you.
Yep.
I just had this question. When you use spectral clustering, for example, if you use k-means, you use something like dbScan, you use something like hierarchy.
Yeah.
Something like dbScan is really good at identifying patterns in the data. What would be that application for spectral clustering, for example, in different shapes of data where clusters come in different patterns, different shapes? Would there be any specific scenario where spectral clustering would be advantageous to be used?
So yeah, so I mean, to me, spectral clustering is really like a general purpose clustering method. So like your cluster could be like this. You really doesn't matter as long as they are well separated and each one is well connected. That matrix will help you separate the two from each other. So basically, the true model behind spectral clustering is really like a manifold for each cluster. Like each cluster can be any shape, right? It could be circles, it could be anything. Otherwise, it's kind of continuous, right? And there are no big holes, no gap, and also the two clusters they don't cross each other. So then I think the main part of spectral clustering is really to be able to embed each cluster into another space. So this will be able to be all here, all here. This one will be all here. So then in the new space, you can use whatever method you like. Like that problem has already been simplified, greatly simplified. So it's really an embedded technique. I think preserve the locality. Like your nearby points will remain together. Then this will force the two clusters to be fully separated. Yeah. And it's a good question.
Other questions?
Yeah.
In your application, applications, you did talk about using spectral clustering in images. And did you find that it's usually good in classifying, grouping images, or you tried it across different things, like probably other applications, which you feel that spectral clustering might be advantageous, or is it just that images are really good when you use spectral clustering? Is that a very common application which you found?
Yeah, so basically for me, like spectral cluster on images is a way to sort the images according to the contents, right? Like these images they contain digits, handwritten digits, 0 through 9, right? So it's really meant to be like an automatic process to group all the zeros together, all the ones together, all the twos together, right? So that's just one way to do it. It's I mean, nowadays probably the neural networks will do much better. Yeah, this is the matrix way, right? So like maybe more like an old-fashioned way now, yeah, to find groups of images. Yeah.
Other questions?
I'm sorry.
Go ahead.
Also, do you think spectral clustering would be advantageous when you use it in something like grouping users based on recommendations? For example, when in a recommendation data set, you have sparse matrices.
Yeah.
Do you think spectral clustering would be really advantageous in that scenario when you have sparse matrices and you're trying to group customers together, probably for recommendations?
So yeah, so I think recommendation and clustering, they are two different tasks, right? But if you use the ratings as features, right, to as features for the customers, then you want to find similar customers. I mean, this will be like a perfect, I mean, very good tool. So basically, what this method is good at is to just take a similarity matrix, right? So no matter what your objects are like, what your features are like, as long as you can define how similar they are for every pair of customers, then the rest will be handled by that process. So
to put into context that, like, first of all, it depends on which type of features you have, right? So it might be that you need the composition of these different Ks, right?
Yeah.
Because it can be that for discrete, you might use the indicator function.
So yeah, any choice.
Right. Exactly, and it can be a combination of that.
Yeah.
Right?
Yeah.
So that's a very good choice.
Right.
Yeah. Because there is a flexibility on the K. So when you want to check the similarity, there is flexibility to this K. Now, this K is used a single K for all the dimensions, right? That can be different from different.
Yeah, you can do better. Yeah, that's.
You can change it according to types of features.
And also that could be empirical. Like if you want to find the networks, right? Say how you want to define similarity between people, right? How do you, which function to use when it's hard? Well, maybe you can see how how many papers they have published together. Right? That will be a similarity, right? The more they publish together, the more similar, right? The two researchers are in terms of field, right? You can just use those counts as your ideas, but it can be empirical. Yeah.
So since you book, okay, Dr. Chen is going to be around for another hour in another setting, not in this room. So you'll get Robert to continue the conversation with him. In the meantime, I think I will just thank Professor Chen for the great presentation, and thank you for attending and for your questions as well.
Thank you. Thank you.